In this example, we're going to determine if a car hits a bicycle at an intersection. This is a great example of the kinematic equations. Besides, as a bicyclist, it's something that I'm keenly interested in. We're going to assume that the car is traveling at constant velocity v sub c. V sub c happens to be equal to 15 meters per second. The car has a length L of 3 meters and a width W of 1.5 meters, and it starts out a distance d, capital D, 100 meters from the intersection. The bicyclist is traveling at constant velocity v sub b, and the bicycle has a length L. We're going to calculate the distances d for which there will be an intersection at a collision at the intersection. The bicyclist is traveling at a constant velocity of 5 meters per second. We've got numeric values for all of these constants, but as is always the case, it's much better to work the problem with symbolic values and plug in the numeric values at the very end. We'll begin by calculating how long it takes the car to reach the intersection. In other words, the car, which is traveling at v sub c, has to reach the intersection a distance d away. We can find this time t by using the first kinematic equation. We can write down x is going to be equal to d, so we can write down that d is going to be equal to the velocity of the car times the time t that it takes the car to reach the intersection. We can easily invert this to find the time. T is going to be equal to d divided by v sub car. Now, what about the bicyclist? Well, to find the bicyclist position, we have to define a coordinate system. So let's define a coordinate which is going upwards in this direction, and we'll call that position upwards starting at this point as 0. We'll call that the variable y. In this particular coordinate system, the bicycle over here starts out at a distance that's equal to minus d. So we can write down the position of the bicycle, actually the position of the front wheel of the bicycle. That's going to be y is going to be equal to its initial position, which is minus d, plus the velocity of the bicycle times the time t that the bicycle is traveling along. Now, of course, if we want to find out if the bicycle is going to hit the car at the intersection, the car arrives at the intersection at a time capital T. So, if both the car and the bicyclist are hugging the curb over here, we can find out where the bicycle is going to be when the car has just moved into the intersection, simply by plugging in the capital T, the time it took the car to reach the intersection, into t over here. So that's going to give us y is going to be equal to minus d plus vb times t, which is also equal to minus d plus v bicyclist times capital D divided by v sub car. Next, we can ask, well, is there going to be a collision? And there will be a collision if the front wheel of the bicycle has just cleared the curb over here. In other words, if the front wheel of the bicycle is at y is equal to 0, we'll have a collision. So we write down 0 is equal to minus d plus v bicycle times d divided by v car. And this is really easy to solve for the distance d that will result in a collision between the front wheel of the bicycle and the front bumper of the car. That's going to be d is just equal to, and I'll rearrange the terms slightly, the ratio of the bicycle velocity to the car velocity times the distance that the car starts away.